Okay, should we get started?
Sure, sounds good to me.
Okay. Well, welcome everyone to this week's CDAC webinar talk. Today it's a real pleasure to introduce Michael Demkowicz, who is the director of one of our sister NNSA Academic Alliance centers, the Center for Research Excellence on Dynamically Deformed Solids. Michael has a bachelor's degree from UT Austin and master and PhD from MIT in mechanical engineering. From 2006 to 2008, he was at Los Alamos, first as a postdoc and then as a member of the technical staff. Michael then moved back to MIT, but joined the faculty and was there for a number of years, moving to Texas A&M in 2016 as an associate professor in the Department of Material Science and Engineering. Michael's research interests include metals and metal composites, including interfaces, which is obviously a focus of his center and which he will discuss today. So thank you for joining us. We're really looking forward to your talk.
Thank you, Russ, and thank you for having me. It's a great pleasure. So today I'll be telling you about solid-state interfaces and their effects on the properties of multiphase metals. As Russ mentioned, some of the work that I'll be presenting to you here was supported through CREDS, which is the Center for Research Excellence on Dynamically Deformed Solids. And there are a couple of other sources of support that I wanted to acknowledge, namely CMIME, which was a DOE-sponsored EFRC, that sort of initiated some of this interface work on a large scale, and also some NSF-supported projects that I have on this. So the people who are most directly responsible for having done the work are shown here on the right. So students and postdocs and various collaborators. So I wanted to thank them in advance, and I'll be citing their work throughout the presentation as well. So by way of motivation, interfaces, our interest in interfaces stems from a desire to better understand, predict, and process multiphase metallic materials. Now, these are just some examples of microstructures in multiphase metallic materials. So this one on the left here is an additively manufactured nickel-based alloy. This one is Inconel 718. And you see that this looks sort of like a patchwork of bright colors. Each of these colored regions is a single crystal grain. And you can see that, with modern methods such as additive manufacturing, you can actually control the structure of these grains to a very great degree. You can dial in their sizes, their shapes, in some instances also their orientations. So, there's a great deal of fidelity that you can achieve in the way that you control the microstructure. In the middle and on the right, I'm showing you two other microstructures. These two are in, the one on the left is, you could say, a single phase alloy. The ones in the middle and right are two-phase composites, where the two phases are copper and niobium in the middle, copper and tungsten on the right. These are materials that are basically made of two phase separating components. And the response of these materials, of course, all three of them, is a function of their microstructure. Part of microstructure is, of course, the composition and the shape and the size of the individual constituents. But an equally important part are the interfaces between those constituents. So one of the quotes that we really like to repeat in our center, and that a lot of my PIs are well familiar with, is the one on the bottom here from John Hirth, spoken in 1972, and just as current today as it was then. If one excludes single crystal research, one could claim that the balance of the field of metallurgy relates to interfacial properties, right? So the properties of the joints where these individual constituents meet. Now, of course, this is true of the response of materials to all kinds of different stimuli, including mechanical deformation, irradiation, corrosion, all kinds of different factors. But in the Center for Research Excellence on Dynamically Deformed Solids, we are in particular interested in high strain rate mechanical response. So just, this is the only, sort of organization slide that I'll show you that's related to the center itself. And that is, we are a center that got started in 2018. We have 4 different institutions. Texas A&M is the lead university. The other 3 are UC Santa Barbara, University of Michigan, University of Connecticut. And our goals are to predict the influence of microstructural heterogeneities, especially interfaces, on high strain rate response. So that's basically all that I'm going to tell you by way of introduction. And the rest of this talk, I'll just sort of go through 3 separate vignettes where I tell you a little bit about some examples of how interfaces influence material properties. Here are the spoilers, right? So I'm going to come back to this at the end of the talk when I sort of wrap up. The spoilers, sort of the big takeaway messages that I want to give you are that interfaces are not just dividing surfaces between grains. They have their own structure, their own properties. Interfaces affect materials' response at multiple length scales, and that'll become clearer what I mean by that in just a minute. And we now have the computational experimental tools to build fundamental physical understanding of solid state interfaces. So let's move on to the first one, interface structure at the composite scale. So let me just make clear what I mean by that. At the composite scale, if you were to look at a composite, here are examples of 2 composites. The one on the left is a composite of copper and tantalum in 50-50 proportions. This one is made by equal channel angular extrusion. It's a kind of processing method that you can use for changing the internal structure of composites. The one on the right is a copper iron composite made by direct metal deposition, which is a kind of additive manufacturing of metals. And in both cases, you can fairly easily see that there are phase boundaries, right? So for example, here are some phase boundaries on the right, right? Those lines that I drew there are phase boundaries. Here are other phase boundaries, the ones on the right, on the left. Within each phase, there are also grain boundaries. So these individual constituents are not single crystals. They have multiple grains inside. And so between all of those grains, there are grain boundaries. So these composites are made up of different phases, but they're also made up of different interfaces. And so the question that we have is, how do the properties of those interfaces then influence the response of the composite? So I'm gonna just give you one simple example of something that we've actually investigated recently within CREDS, just to give you a sense of the kind of effect that interfaces can have. So I'll just briefly tell you about some finite element modeling that we did. So this is a FEM domain, a simulation domain that we investigated, where we put in a crack. This initial crack could be there from processing, it could be there from deformation, it could be there through a variety of environmental factors as well. And we applied a far field tensile strain on this model by applying tractions at the end of this sort of large region 2, which was sort of coarsely meshed so as to conserve computational resources. And then on the inside, we had region 1, which was more finely meshed. And if you blow it up and look at, sort of zoom in and see what it looks like, we actually made it so that it was made up of a microstructure, a tiling of hexagonal grains. And so you can orient a tiling of hexagonal grains in different ways. So we had orientation 1, which is the one that you see here in the middle. We also had a different orientation, orientation 2, which was a 30-degree rotation of the one on the left. And we investigated, how does the crack run through these microstructures? So to give you a very simple sort of perspective on what happens, here is a crack that runs through orientation number 1, when all of the grain boundaries are exactly the same type, right? So let's say they're all equally strong, and the crack is oriented sort of for easy propagation along the interfaces between these grains. This solid very easily undergoes intergranular fracture. If you look at orientation 2, which is what I'm showing here, the crack now takes a somewhat more tortuous path. It's harder for it to go from the left to the right, basically because this particular orientation is not as conducive for a very straight crack to run directly across. So you see a little bit more tortuosity, a little bit more deflection, but overall it's just a single crack that runs from left to right, okay? What we did then is we started introducing into this model elements, in particular interfaces that have a different strength from that of the yellow interfaces here. So the yellow interfaces that I drew here, you can see some of them here as well. Those are strong, what we call strong interfaces. And then scattered throughout these models on the right, you'll see a couple of instances, isolated instances of red interfaces, and those are weak interfaces, right? So we scattered in occasional weak interfaces, and then we repeated this model. We repeated the simulation to see what happens. And in short, what happens is that you see that this crack, so this is orientation 1, the crack that ran straight through in orientation 1 now takes a more tortuous path. It's more difficult for it to get from left to right. And in fact, you see occasionally, for example, here and here, you see occasionally situations where a daughter crack is nucleated or where the crack branches into a different direction. It's even more pronounced in the case of orientation 2, which is what I have here on the right. In that case, it becomes even more difficult for the crack to make it from the left to the right without branching and without creating daughter cracks. So those sorts of phenomena are the direct impact of having a certain admixture of weak interfaces. Now I seem to have lost my cursor, so I'm not really sure what happened here. Let me see if I can fix this. There we go. Okay. My cursor seems to have disappeared and my computer is now unresponsive. This is not a good sign. Do you guys still hear me?
Yes, we hear
you. Still okay, well that's good. But unfortunately I can't advance anything, so I'm not really sure what happened here.
Oh.
Huh. I apologize, this has not happened to me before. Oh, now it's back. Okay. So in addition to these visualizations that you see here of how the cracks are propagating, we can also plot out some quantitative information. So all these plots above are showing you stress intensity. So basically it's a stress intensity as a function of the model geometry as well as the applied stresses, the stresses that have been applied in the far field. And this stress intensity tells us about how easy it is for the crack to propagate. So, you know, you can think of a plot of stress intensity versus the crack length as a kind of equivalent for a stress strain curve in the case of fracture. And what we can see in all of these simulations is that the stress intensity initially goes up and then sort of reaches an asymptote when the crack is ready to propagate, you know, in a sort of fast manner, just sort of run across the model. And so sort of this asymptotic stress or critical stress is something that characterizes for us the toughness of the material, right? Or in other words, its resistance to fracture, if you will. So let me show you, oops, geez, this thing is just not cooperating today. Okay, so let me show you some simulations. So this is just a movie of one of those cracks running through. And you can see that it sort of starts out kind of, you know, barely moving along, and then suddenly it shoots across as soon as it reaches that critical stress intensity. And if you look closely, you can actually see the daughter cracks and the branching events occurring as this crack tries to propagate from left to right. Same thing here, you know, this is the other orientation. You see a little bit more in the way of daughter crack nucleation. You see a big branch here, and then basically this other branch with additional daughter cracks moving off to the side. The upshot is that now that we've figured out how to do these simulations and, you know, how to analyze them and figure out the critical stress intensities, we can actually plot those critical stress intensities as a function of the fraction of strong grain boundaries versus weak grain boundaries. And we get to a very interesting conclusion. So this is the critical stress intensity normalized by the stress intensity for a uniform microstructure that contains only the strong boundaries, okay? And you can see that the critical stress intensity actually is not optimal. It's not highest when all of the grain boundaries are strong. In fact, the highest toughness occurs when you have a certain admixture, a minority fraction, let's say 10 to 20% of weak grain boundaries. Okay, so this red curve here is showing you how the toughness evolves as a function of the admixture of weak grain boundaries. And then we also looked at another type of grain boundary which we call very weak, which is basically, you know, a weak grain boundary that has even lower intrinsic toughness, and that's the black curve up here. And so, as you can see, there is this sort of admixture that you can put in here of weak grain boundaries that actually toughens the material. And moreover, as you go from you know, when you take that admixture of weak grain boundaries and you make them weaker, this toughening effect becomes more pronounced, right? So the weaker you make the boundaries, the tougher the overall composite becomes. This is for orientation 1. For orientation 2, we see a similar trend. Here, the sensitivity to the weakness of the weak grain boundaries is not as pronounced, but you can still see that the optimal toughness is reached when you have 10% admixture of weak grain boundaries. And in this range, the toughness increases as you make the boundaries weaker. So in other words, this sort of has important implications for us because it shows us that the toughest materials actually incorporate a minority fraction of weak boundaries. Flaw-free microstructures are not optimal. And so if you're processing multi-phase metallic materials, that's good news, right? On the one hand, it means that you don't have to strive to eliminate all flaws. On the other hand, it means that if you have made a material that, you know, is relatively flaw-free, then as it deforms and new flaws are formed, it might actually get tougher. Now, that's of course assuming that you don't exceed some critical fraction of those weak boundaries. When the boundaries all become weak, then the material becomes weak as a whole. But there is some range of weak grain boundary fraction that will actually toughen the material. So this is an example of an investigation that shows us how connectivity of boundaries at the scale of the composite, at the scale of the overall composite structure of the material, influences the properties. So I'm going to move on to, and that was vignette number 1, if you will. I'm going to move on now to the second vignette. The second vignette is going to deal with what I would call the mesoscale. The mesoscale is the origin of the word meso means intermediate, between, right? So basically this is the scale between scales. The between is you're sort of higher than the atomic scale, but you're lower than the overall composite scale. So typically a lot of times people will associate the mesoscale with micron level dimensions. So micrometer level dimensions in the case of metal microstructures. And at this mesoscale, we are interested not only in the overall structure of the composite, but also how the individual boundaries in that composite behave. So in this particular vignette, just to illustrate for you how we do investigations on mesoscale properties, I'm going to describe to you a study that we did on a nickel-based superalloy. This one is Inconel 725. This particular sample that you're looking at here on the left is about, I apologize for the missing scale bar, it's about 1 centimeter in diameter. And it was tested to failure in tension after charging with hydrogen. Some of you might recognize hydrogen as an embrittling agent, right? So hydrogen makes things more brittle. When something fails after it has been embrittled by hydrogen, when a metal fails under hydrogen embrittlement, oftentimes it fails along the grain boundaries. And so that leads to intergranular fracture. The question then is, which grain boundaries are the weak ones and which ones are the strong ones? So to answer that question, you now have to go down, descend to the microstructure level, and rather than focusing on how the boundaries are connected, you focus on the individual boundaries. So what you see here on the right is an EBSD scan, electron backscatter diffraction scan, taken in an electron microscope. And in this particular scan, you can actually observe individual grain boundaries. Right? So for example, let's say I have, let's do it again. Oops, I can't see my cursor. I can't annotate very well, guys. I'm sorry. This right here, for example, would be an individual grain boundary. And we might be interested in figuring out how that individual grain boundary is going to embrittle. Is it going to be one of the stronger boundaries, or is it going to be one of the weaker boundaries? And so mesoscale studies are the ones that are going to help us to figure that out. Okay. I think this annotation is what makes everything go berserk. Okay, so if we are interested in characterizing individual grain boundaries, one of the first things that we need to think about is the grain boundary crystallographic character. So let me give you just a very brief introduction to grain boundary crystallographic character. This is basically, you can think of this as describing the large scale, the macro scale degrees of freedom of a grain boundary, the fewest number of degrees of freedom that you need to actually specify the character of the boundary. The way that we do that is we imagine a crystalline grain, illustrated here on the left as a cube, oriented in some reference frame. So this is XYZ, that's my reference frame. And this is going to be one of the two grains that meets at a grain boundary. The next thing that we have to specify is the orientation of the second grain, the other grain that forms the grain boundary, because a grain boundary is a place where two grains join. Okay, so the way that we're going to do that is we're going to envision another grain which is oriented differently from the first one. Now, of course, we could also think about a grain that is oriented identically to the first one. However, if we take two identically oriented grains and we join them, we just get a bigger grain, right? Because, you know, if you're looking at grain boundaries, or what are called homophase boundaries, so boundaries between identical phases, you join, if the two phases are oriented identically, you join them, you just get a single crystal of larger dimensions. However, if these two phases are oriented differently in space, right? So if this second one has a different orientation in space from the first one, then when I join them, they're not going to make a perfect joint. The atoms at the joint are going to be differently dispositioned in these two grains, and I'll get a grain boundary. The way we describe this difference in orientation is by describing the relative rotation, the rotation that you would have to apply in order to rotate the grain on the left into the configuration on the right. We can do that by giving a rotation matrix, R. There are other ways to describe rotations as well. However, no matter what approach you choose to describe this relative rotation, the number of independent parameters that you need to specify that rotation is always 3. So some of you may be familiar with Euler angles. You need 3 Euler angles to specify a general rotation. Others may be familiar with the idea of an axis angle representation of a rotation. Again, you need 3 parameters, 1 for the angle and 2 for the axis orientation. So to specify an arbitrary rotation in 3D, you need 3 degrees of freedom. Okay, these 3 degrees of freedom are called the misorientation of the grain boundary. The other thing that you need is the orientation of the grain boundary plane. Okay, so basically the plane in space, the orientation of the plane along which the two boundaries are going to be joined. Mathematically, whenever we describe plane orientations, we do that using a unit normal vector. And of course, in 3D, the number of independent parameters that are needed to specify a unit normal vector are 2. So there are 2 degrees of freedom associated with the grain boundary plane orientation. Altogether, we have 5 crystallographic degrees of freedom for a grain boundary. So the crystallography of a boundary forms a 5-dimensional space. Each individual point in that 5-dimensional space describes a distinct grain boundary type. Okay, so there's a very large space of crystallographic characters that boundaries can live in. Each one of those boundaries with distinct crystallographic character can have different properties. Okay, so this is one of the challenges of investigating grain boundaries. You have this relatively high dimensional space to explore. Just to finish the thought here, once you have this grain boundary plane orientation, once you have the orientation of the two grains, what you do next is then you imagine cutting each one of those two grains along the boundary plane facet direction. Right, so imagine that I take this plane, I use it to cut this boundary, I use it to cut this grain, I then cut this grain with the same plane orientation. You get these sort of facets that form, and then you can join those two grains and you get a grain boundary. Okay, so this is how we think about describing the crystallography of grain boundaries. Okay, in theory that's nice. How do we actually investigate that experimentally? Well, one way that you can do it is you can do 3D X-ray grain mapping. So the capability to do something like this is available, for instance, at the Advanced Photon Source at APS. This approach basically uses diffraction. It illuminates a sample of about millimeter scale dimensions. It then measures all the Bragg reflections from the different grains at different distances from the sample. And by extrapolating a line through the points at a given Bragg reflection, you can actually locate in 3D the location of the corresponding grain in the sample. And of course, you get lots and lots and lots of these spots. And so you have to somehow figure out the data analysis of how you're going to analyze all these diffraction images. That's really the main difficulty, the analysis of this kind of data. But once you've gone through the analysis, you get a 3D reconstruction of the grain structure. And here's an example of one of those 3D reconstructions. Each one of the individual sort of patches of different color that you see here is a distinct grain. So you get both the shape of the grain, its location, as well as its crystallographic orientation. So this is a very powerful technique. We use this technique to study the sample that I showed you before. So here's that tensile specimen. We cut out millimeter diameter samples out of that specimen. This is just a sort of top view of where we cut those out. This is the 3D grain reconstruction that I'm showing you on the bottom. The technique, as it's called at APS, is high energy diffraction microscopy, or HEDM. At the same beamline, you can actually do X-ray absorption tomography, which is very nice because you need that to actually map out, you know, if you're studying a specimen like the one that we had here that has this big internal crack, you actually need this X-ray absorption tomography to plot out the shape of the crack. And then you can actually correlate these two 3D reconstructions. You can register them, you can put them into registry with each other, and then you can figure out what are the sizes and shapes and orientations of all the grains along the entire crack face in this sample. So this is a very powerful technique. What we found when we did this study is that if you look at how the crack is progressing through the material, so in this particular image, the crack is coming from the right and moving to the left. There are a number of crack deflection events where the crack is propagating along a grain boundary. It encounters another grain boundary like this one, which seems to be very favorably oriented for the crack to continue propagating along it. But instead of propagating along this grain boundary, what the crack does is it goes around the grain, it takes a detour, right? Circumventing this boundary, this grain boundary, avoiding it, in other words. So these crack deflection events, when they occur, signal to us that this particular boundary, right, the one that the crack is avoiding, is especially strong. Right? This is an especially strong boundary. And of course, because the reconstruction that we have here provides us with both the shapes, locations of the grains, as well as their orientations, their crystallographic orientations in space, we can actually back out the complete 5-dimensional crystallographic character of this boundary. So this particular boundary, for instance, has a misorientation that can be described with this angle axis pair. And it has grain boundary plane orientations that can be written down using Miller indices in coordinate frames fixed in the two neighboring grains. So in one of the two grains, the facet plane is an 001 type plane, and in the other grain, the facet plane is a 111 type grain. Okay, so we get the full crystallographic character. We found 10 such crack deflection events in that particular study and on that particular sample. And then we looked for commonalities, and we saw that all but one, so out of those 10, 9 of those strong boundaries were occurring along boundaries whose facet planes were of a low Miller index type. So by low Miller index, I mean 001, 011, or 111. We call those kinds of boundaries with low index planes, or blips. And all the ones that are shaded gray here, you can see that at least one of the two planes is a low index plane. So all of these have 111 type low index planes. This one has 001, 001. Here, this one would not be considered a low index plane. This is just for grain 2. If you look at grain 1 has a low index plane, 101. And then here is a 123, which we would again not consider low index, but the matching grain is a 111, so that's low index. There was only one strong boundary whose plane was not a low index plane. Okay, so this is a very good sort of correlation between the strength of boundaries and their crystallographic character. Okay, so this is an example of how we can study grain boundaries at the mesoscale, at the level of individual grain boundary properties. So that's vignette number 2. Let me move on to vignette number 3, where we are now studying interfaces at the atomic scale, looking at their structure and properties at the atomic scale. So once we know the crystallographic character of a boundary, one of the things that we can do is we can create atomistic models, right? We can, once we know how to orient the two neighboring crystals, how to orient the plane along which they're joined, we can actually make a model of those boundaries. So here are just some examples of boundaries in alpha iron that I created using simple atomistic modeling tools. And what I want to be able to show you is a simple scheme for classifying interfaces according to their atomic structure. Now, I have to give you a caveat, right up front, that this is not the only way to classify the structure of grain boundaries or interfaces. Okay, there are other ways, there are other approaches. However, I wanted to introduce you to this approach because it's, in my opinion, fairly robust, and also because I wanted to talk about this middle class of interfaces here that I'll introduce to you in just a moment. So what I'm showing you on the left here is a coherent sigma-3 twin boundary in alpha iron. Alpha iron is a BCC, body-centered cubic material. This coherent sigma-3 twin boundary has a boundary plane along 112 type facets in both of the two neighboring grains. This top figure shows you a view of that boundary looking edge on, right? So this sort of region right here is the actual grain boundary plane. And you can, if you look closely, you'll see that you have rows of atoms coming in sort of diagonally here on the bottom, and then they're coming out diagonally on the top, but in the opposite direction. That's sort of a characteristic of twins. And twins, you can think of them as sort of mirror reflections of grains about a particular plane. So in this case, you've got a mirror reflection of the grains of the structure of one grain about a 112 plane. That's a twin boundary, right? Over here on the bottom, I'm showing you a view of just the atoms that are right at the grain boundary plane. So if I were to just cut out the atoms right here at the plane and take them and flip them over by 90 degrees so that rather than looking edge on, I'm looking into the plane of the boundary, this is what the plane of the boundary looks like. And what you can see is that it's very well ordered, right? So the atoms are basically matching on both sides. There really isn't much in the way of straining or under or over coordination of the atoms. They're all fairly happy sitting at this coherent sigma-3 twin boundary. I was lucky enough in this particular model to catch a twinning dislocation. That happened, just willy-nilly by itself. It's not intentional, but it sort of is a nice illustration of this kind of defect that can form at a coherent twin boundary. If I were to take this coherent twin boundary and change its crystallographic character just a little bit, so take the top grain, for instance, and rotate it a little bit, let's say by 5 degrees, around an axis that's perpendicular to the grain boundary plane. So I'm just going to do a relative twist of these two boundaries just by 5 degrees. As soon as you do that, the structure of the interface changes. So here's the plane again, okay? And just looking at it, you can see that it's not nearly as flat and sort of strain-free as the one on the left. And here on the bottom, if you look into the plane of the boundary, so perpendicular to the plane, you can see that there's now a very distinct structure. You've got these patches here of very good atom-to-atom matching. We would call those coherent patches. And those coherent patches are separated by lines of misfit. Turns out that you can actually describe these lines of misfit separating the coherent patches as misfit dislocations. So I think many of you may be familiar with dislocations from studies on single crystals, plasticity, things like that. You can actually see these misfit dislocations forming at low angle semicoherent boundaries, such as this one. If I were to then continue to increase the twist, if I were to continue to increase the relative misorientation by increasing the relative twist of those two grains, what happens is that these misfit dislocations get closer and closer together. The coherent patches between them get smaller and smaller. Eventually, the misfit dislocations begin to overlap, and you get something that looks like this on the right. So in this case, I've taken this coherent twin boundary, I've imposed a 30-degree twist, so a relatively larger twist angle. And as you can see, there's really no evidence of coherency here anymore. You might not say that this boundary is completely disordered, right? So if you look closely, you can probably convince yourself that there's some vestiges of order in there still. But it's definitely not a coherent boundary, and you can't really sort of identify coherent patches that are separated by line defects either. So this is what we would call an incoherent grain boundary. So a lot of work has gone into studying all of these different boundary types, but I wanted to give you just a little bit of a vignette, a little introduction into work that we've done into studying semicoherent interfaces of the type that I'm showing you here in the middle. So in other words, these are interfaces where the crystallographic character allows for the structure to develop into a series of coherent patches separated by misfit dislocations. Here's an example of the internal structure of a silver vanadium heterophase interface. So again, just like with the alpha iron boundary that I was showing you a moment ago, this one can be viewed as consisting of coherent regions separated by misfit dislocations. We can, one of the nice things about these semi-coherent interfaces is that we can actually be quantitative about describing the structure, for example, in terms of the spacing between the dislocations that are found at this interface, their direction with respect to the crystal orientation of the two neighboring grains, the Burger's vectors of those dislocations. Those are all quantitative ways of describing the structure. And all of these different quantitative features of the interface structure are actually related through an equation that's known as the quantized Frank-Bilby equation. I've written it down here on the left. I'm not going to go through it. I could give you a whole separate talk just talking about the qFBE. Very interesting equation, very powerful in predicting the internal structure of these semi-coherent interfaces. Instead, all I'll tell you is that if you work on solving this equation, you can actually predict analytically what the configuration of dislocations at the interface should be. So on the left, I'm showing you an analytical prediction of the interface of the predicted dislocation, misfit dislocation configurations at this specific interface on the right. So you can compare the analytical prediction on the left to the atomistic simulation on the right, and they match really well. Now, because these lines that are in this model are nothing other than dislocations, and dislocations are very, very well studied, very well understood, you can, for instance, calculate in detail, analytically, what are the stress fields of this dislocation? What are the stress and strain fields that are surrounding these dislocations? And from that, you can figure out what are the stress and strain fields surrounding the interface. Right? If the interface is just made up of a bunch of dislocations, and you know how the dislocations behave, then you can actually figure out the stress and strain fields around the interface. Once you know the stress and strain fields around the interface, you can calculate the energy of the interface, or at least the strain energy of the interface, the contribution to the interface energy coming from these dislocations. Okay, so The upshot is that now you can actually make models that are quantitatively predictive, that can predict for you interface energy, for instance. So here's an example of a calculation that we did, again, on this silver vanadium interface, like I showed you on the previous slide. And we selected interfaces where the silver facet was the 111 type plane along the interface, and the vanadium facet was a 110 type plane. And we considered various different twist angles. So you can imagine taking this cylindrical model and then imposing a relative twist to study different orientations. And then we could actually calculate the energy of this interface as a function of the twist angle using atomistic models. So these open circles that you see here are molecular dynamics simulations that show you the energy of those interfaces as a function of the twist angle. And for the corresponding crystallographic character, using the dislocation-based model that I just told you about, we could actually calculate the interface energy. And that's this solid red line, the thick red line that you see here, is actually our analytical prediction of how the interface energy varies with the twist angle. And as you can see here, we are quantitatively accurate in predicting this to within millijoules, tens of millijoules per meter squared. So these are extremely accurate models that you can use to predict the energy of the interfaces as well as their internal structure, while basically circumventing atomistic models. So this is one way that you can actually describe interface properties using dislocation models. Let me give you another example of how you can describe interface properties using dislocation models. So for this particular illustration, I will talk about these two types of composites. The composite on the left is a copper-niobium multi-layer composite. So what you're looking at here is a transmission electron micrograph through a metal laminate where you've got alternating copper, niobium, copper, niobium, copper, niobium layers. Each of them is about 75 nanometers thick, so relatively thin layers. These were made by physical vapor deposition. And here on the right, you see another TEM micrograph of another copper niobium composite, again, a laminate. So the alternating layers here are copper, niobium, copper, niobium, copper, niobium. The difference is that while this one on the left was made by physical vapor deposition, the one on the right was made by accumulated roll bonding. And accumulated roll bonding is something that you guys might be familiar with from the idea of making a katana, for instance, like a samurai sword, where they would flatten it out by hammering it, then fold it in half, and then flatten that out again, and then fold it again. So basically you're stacking layers of material, rolling them out so that they're flat like dough, okay? Then you're cutting them, stacking them again, rolling them out again. You do this over and over and over again. You end up with a very well bonded, very high perfection multi-layer composite like the one that you see here, right? So these are both metal laminates. The difference is that they're made by different processing routes, right? So, and the fact that they're made by different processing routes results in different crystallographic characters of the interfaces that form between these copper and niobium layers. In particular, for the ones on the left, the physical vapor deposited ones, we can describe the interfaces as forming along closest packed planes. So if you look at the copper layers, the interface plane is the 111 type plane. The niobium layers, the interface plane is the 110 type plane. And if you join those two planes together, you'll get the interface of the type that we see in the physical vapor deposited layers. However, in the accumulated roll bonded layers, you get the same relative orientation of the copper and the niobium crystals. However, the plane orientation, so the Miller indices of the facet planes that join on the interface are different. 112 in copper and 112 niobium. So different from what they are in the PVD case, right? So the ARB interface planes are different than the PVD interface planes. And it turns out that this has an enormous influence on the properties of these interfaces. So if we were to look at the PVD interface, here's the PVD interface, again, looking edge on over here, On the right, I'm showing you a top-down view looking into the interface plane of this copper niobium interface. You can already see just by eyeballing it that it has this sort of quasi-periodic structure in it. Okay, but if you do a more detailed analysis, you can figure out that this quasi-periodic structure is the outcome of dislocation, misfit dislocations that are present in this microstructure, or in this interface structure. So this particular interface contains two sets of dislocations. This is one set. This is the orientation of one set of dislocations. Here's the orientation of the second set of dislocations. And all those little places here where you have near perfect coincidence between a copper and a niobium atom are actually the intersections between those dislocations. So those are misfit dislocation intersections. Now, an important fact about this particular interface is that both sets of dislocations in this interface have Berger's vectors, indicated here by these arrows, that are entirely contained within the interface plane. So these Berger's vectors are completely within the interface plane. They have no component pointing out of the interface plane. Those of you who are familiar with dislocation mechanics recognize that when you have an interface, when you have a dislocation with a certain direction and a certain Berger's vector, the plane that is defined by those two vectors is the glide plane of the dislocation. Right, so the glide plane of the dislocation, the plane along which the dislocation can easily move, is the plane that contains the line direction and the Berger's vector. So in the case of these particular sets of dislocations, the glide plane of both sets of dislocations is the interface plane, and that's a fairly important feature of this interface, because of what it means is that now if I take this interface and I apply shear stresses to it, this interface is actually very, very weak in shear. It can slip, these two neighboring crystals, the copper and niobium crystals, can slip past each other extremely easily. So, you know, we've actually done simulations where we've applied shear stresses on the copper and the niobium side pointing in different directions within the interface plane. We've plotted out a sort of yield surface. So in other words, the critical stress that's needed to make the interface move as a function of the applied shear direction. And those, the shear resistance of this interface is, regardless of the direction, is never more than a few hundred megapascals. And the strongest direction is about 1.2 gigapascals, so 1200 megapascals. By the standards of shear resistance, this is a very low number, right? So this interface slips very easily, and it's a direct consequence of the way that the dislocations in that interface are configured, right? Here's the other interface that I was telling you about. This is the ARB interface, so accumulated will bonding interface. Again, here's the edge-on view, and here's the top-down view. This interface is also made up of dislocations, so you can actually, if you look carefully, you can actually see in this edge-on view that there's locations here where you've got 3 planes coming in from the left, joining with 4 planes on the right. So that tells you by itself that there's got to be an edge dislocation somewhere in there, right? So, and indeed, if you look through, there's a bunch of locations where there's an edge dislocation. You can actually figure out the Berger's vector of that dislocation. It happens to point in this direction. And looking at it, you can immediately see the Berger's vector of this dislocation has a component that points out of the interface plane. Okay, in other words, the glide plane of that particular dislocation is not going to be the interface plane. Here's another set of dislocations that is present in this interface. This one also has a Berger's vector that points out of the interface plane. This one also is not going to glide easily in the interface. If you look top down, there's a third set of dislocations. And, you know, I'm sorry, I'm sort of telling you this, information about the locations of the dislocations kind of, without proof, if you will. But, you know, maybe just to sort of assuage your curiosity, there are actually rigorous ways of showing that these dislocations are indeed present in these interfaces, as well as figuring out what their Berger's vectors are. And this particular set of dislocations has a Berger's vector that actually is contained entirely in the interface plane. So in other words, we have two sets of dislocations with Berger's vectors that point out of the interface plane, one set of dislocations with the Berger's vector that is in the interface plane. This interface is going to be able to slip very easily in the direction of this Berger's vector. And in the perpendicular direction, it's not going to be able to slip very easily at all. So in other words, this one is going to have an extremely anisotropic shear resistance envelope, if you will, or a yield surface. And you can make that prediction based entirely on the dislocation-based structure of that interface. Again, we did atomistic simulations to confirm that, and indeed it turns out that along the Berger's vector direction that is contained entirely within the interface plane, there's really very little in the way of shear resistance. So these symbols here indicate for you the location of the envelope for slip along the Berger's vector direction within the interface. And then along this direction, the horizontal direction here, you basically have no slip. And this, instead of slipping, what happens is that this interface actually begins to emit dislocations into the neighboring crystals. So in other words, if you were to start applying shear stresses to this interface along the direction perpendicular to this Berger's vector that I showed you here, you will actually see partials getting emitted from the interface and then gliding into the neighboring crystals. So in other words, rather than slipping, this interface prefers to make the neighboring materials yield, so the neighboring crystal and grains yield. And so the structure of this interface has a very direct and profound influence on the mechanical properties, in particular the shear resistance. So with that, I wanted to end my last vignette. I'm going to go back to my takeaways. The takeaways are precisely the spoilers that I was showing you at the beginning, except now with a little bit more detail in them. So interfaces are not just dividing surfaces between grains, they have their own internal structure and properties, and I gave you examples resulting from the connectivity of interfaces, their crystallographic character, as well as their defect-based structure, internal structure. Interfaces affect properties at multiple length scales, so I showed you examples from the composite scale, the mesoscale, and the atomic scale. The other, I think important observation that you can make, and this is very clear when you look at the field of interface research today, is that we now have the computational and experimental tools to actually build up a fundamental physical understanding of how solid-state interfaces work. This was not the case only about 20 years ago or so. There was very little that you could do quantitatively in studying interfaces, but now we have advanced processing and testing methods that allow us to do small-scale tests, make materials with controlled interface distributions and things like that. We have electron and X-ray characterization methods that allow us to plot out the shapes and orientations of microstructures in 3D. And we have multi-scale modeling methods that allow us to actually simulate the way that interfaces will behave, going all the way from the atomic scale to the scale of the composite itself. So with that, I wanted to thank you for your attention, and I'm happy to take any questions you might have.
Thank you, Michael, for a very nice talk. Are there questions for Michael? You can use the chat or just unmute yourself.
Hello, Russ, can you hear me? This is Kevin D'Amico speaking.
Yes, go ahead, Kevin.
Hi. No, that was a great talk. I really like the way that you talked about the sort of 3 different length scales. I had kind of questions on each one, but just the first one that occurred to me when you were talking about the sort of macroscopic scale. Mm-hmm. I think the phrase that you referred to was the toughness of the interfaces or the toughness of the boundaries. Mm-hmm. Is that right?
Yeah.
So how does that relate to sort of the macroscopic hardness property of a material, and how does something like quenching affect that property? Is the hardness related to the toughness? Hardness of a material related to the toughness, and is that something that you would expect would be influenced by quenching type practices or behaviors? So
to first, I think that answering that question in detail it would take a long time. But let me just give you a 0th order answer here. So hardness is a property that has to do with the resistance of the material to plastic deformation.
Mm-hmm.
Toughness is a property that relates to the resistance of the material for propagating a crack. It turns out that, for many materials, those two properties are related in an inverse fashion. Namely, the harder a material is, the less tough it is. So in other words, the more difficult it is to plastically deform a material, the easier it is to propagate a crack. And conversely, the softer a material is, right? So the easier it is to plastically deform, the more difficult it is to propagate a crack. Mm-hmm. So there's this sort of trade-off, and it has to do with the fact that when you think about what gives a material toughness, right? Especially in the case of metals, what most of the toughness of the material originates from plasticity occurring near the tip of a propagating crack. Right, so the plasticity that occurs near the tip of a propagating crack will actually dissipate away energy from the crack. It'll impede the crack as it travels. And so the easier it is for something to plastically deform, typically, the more difficult it is to propagate a crack through it. Mm-hmm. So one of the big challenges in materials science, and this has been a long-standing challenge for many decades, is to try to get away from that kind of trade-off to create materials that are both tough and hard, and that's not easy, right? So there are strategies that people have come up with, but as a rule, as a sort of 0th order response to there is this sort of trade-off between those two properties.
Very good, thank you. Thank you.
Thanks. More questions? I have a question about the underlying force model you use in your atomic scale simulations. You didn't describe that, and how robust is it, and how well validated is it? So in terms of atomic structure and so on.
Sure, yeah, so that's always a big question with atomistic models. For all of the examples that I showed you here, we were intentionally dealing with combinations of metals that we are confident we can model accurately using atomistic methods. So the models that we use here for these, for example, copper and niobium. Copper is an FCC material that is very well represented using embedded atom potentials, extremely well represented using EAM potentials. Niobium is a BCC material that is adequately represented using EAM potentials, although not as well as copper, okay? Copper niobium, the binary system, has very limited solid solubility. So copper and niobium are like water and oil. They don't mix, they tend to phase separate. So that means that there's very little solubility. They don't form compounds, they don't form intermetallic phases. And so constructing a potential that actually reproduces that kind of simple phase diagram is not too difficult, okay? And you can easily show that your potential reproduces that kind of phase diagram. So for this kind of binary system made out of two elements that we think we can model well, and having very little chemical complexity in and of itself, we think that these models are actually pretty good. And correlating the predictions that we've made from simulations to things that have been done experimentally, we can actually make direct comparisons thanks to that. Now, if you were to go to something more complex, like let's say we were to replace niobium with zirconium, things get much more difficult, because zirconium has, I don't know, a dozen intermetallic phases with complex crystal structures, and it's really difficult to come up with a potential that's going to represent that well. Our solution to that has basically been not to study copper zirconium and to focus on things that we can actually model and make that, correlation between the experiments and the simulations.
Mm-hmm. More questions? Thank you.
Yes, I have a question about your different simulations. So you mentioned that you have these 3 different scales. When you do your simulations at the sort of the longer length scale, are they completely different sort of models of the simulations, or are the techniques and sort of mathematics just transferred upwards.
No, the models are generally completely different. And passing information from one type of model to another type of model is one of the big challenges of multi-scale modeling. So, for example, this model that I'm showing you here, this is an atomistic model. The entities that you track here are the locations of the individual atoms, and by atoms we mean the nuclei. So this particular model doesn't track electrons separately, although there are, of course, DFT simulations that you can do that do track electrons. Okay. Meanwhile, in a model such as the one I was showing you before, like these models, right? These models are finite element models, so they represent the material as a continuum, and they homogenize, they average over the properties. They assume that every point in this model can be thought of as a representative volume element of the material, and so that the response of that material is going to be described using a generalized Hooke's law for elastic behavior, and in this case, J2 plasticity for the plastic deformation behavior. And it's solved. The numerical method for solving this model is going to be a partial differential equation solver, such as the finite element method, whereas to work with that atomistic model, we would use ordinary differential equation solvers, to propagate the atoms forward through time along their trajectories. Right, so completely different, you could say, simulation approaches. And the big question is for us, how do we extract information from the atomistic scale and then inform this higher length scale with that information? That's really the challenge of atomistic modeling. And I would say that's where a lot of the effort goes. Running these simulations these days is not terribly difficult. The codes have been developed. We understand how they work. We can adjust them to the properties that we want. The real difficulty and the real challenge is in extracting information and then figuring out a way to pass it across scales.
Thank you.
More questions? I guess I was impressed by the work that's going on at APS and how you're using it for the tomography and microscopy. So that's really very exciting, and it also overlaps some of our interests. We use the APS, and our interests in our center overlap a lot of these that you described.
So this was the I1D beamline with Peter Kinesse was the one in charge of it. It was a very interesting experiment. I think that we were probably the first group of users that was not part of the development team. And the experiment took a few days, and then the analysis took a few years.
Yeah, multigrain diffraction is also a growing area for in situ high pressure, and that's being done at HPCAT. Another sort of validation point maybe concerns when you calculate an interfacial energy, for example, to what extent can you validate those kinds of predictions, say with calorimetry? Can you extract that information calorimetrically?
Not that I'm aware of, not through calorimetry, at least not conventional calorimetry. These days, people have developed also miniaturized calorimetry measurements. Used Plasek at Harvard, for instance, has this sort of calorimeter on a chip that they use. However, I'm not familiar with, and I've talked to him before about, whether it would be feasible to do calorimetry on individual interfaces. Honestly, it's still rather out of reach. The way that interface energy determinations have typically been validated experimentally is by looking at variations in contact angles at triple junctions between multiple surfaces. So let's say that you have a grain boundary or an interface that comes out onto a free surface. If you know the surface energies of the facets that are coming out on the surface, then you can look at the angles of the surface with respect to the grain boundary that forms at the groove on the surface. There's a little groove that forms at the surface. And if you look at those contact angles, you can figure out the relative energy of the boundary relative to the energy of the surface. So that's typically how people have done those kinds of, and actually I might be able to give you sort of an illustration of that here. Right? So if you look closely, right, here are some 3-point contacts between copper niobium interfaces in this multi-layer composite made by PVD. And you can see how there's like a contact angle.
Right.
Right. So there's this interface here, and then there are these two interfaces here. By measuring those contact angles, you can figure out the relative energies of those interfaces. And if you can calibrate at least one of those interface energies, then you can figure out the other ones. That's typically how people have done it experimentally.
Right. Thanks. More questions? Okay, if not, thank you once again, Michael.
Certainly.
Great talk. Thank you all for joining us. There won't be a
Thank
talk
you.
this week because of Thanksgiving. We'll see you in 2 weeks.
Happy Thanksgiving, everyone.
Thanks again.
Bye-bye.